Looking for concavity, then what am I chasing, the first or the second derivative? I'm chasing the second derivative. So if I'm chasing the second derivative, I'm going to take a look at D here. First thing I'm going to do is do h prime of t, so I'm going to do my first derivative. What does my first derivative tell me?
Your critical points.
Tell me my critical points. Are my critical points always maxima and minima? No. There are times I get critical points and it is not a maxima or minima, I just get a critical point. So I'm going to do my first derivative. The derivative of 2 is 0. The derivative of cosine is negative sine. Now if I wanted to know whether or not I had a maxima or a minima, I would set that thing equal to 0 and solve. And that'll give me my locations of possible maxima and minima. It also gives me my critical points. But I'm not chasing that on this. I am chasing the intervals or the points of inflection. So I'm going to do the second derivative, so h double prime of t, which is going to be negative cosine of t. Now I set that equal to 0 to get my critical points. So my points of inflection. So negative cosine t is equal to 0. So cosine t is equal to 0. So I get my unit circle out and I look to see where cosine is equal to 0 on the interval from negative pi to pi. So where is the cosine equal to 0 from negative pi to pi? So negative pi over 2 and pi over 2. Okay? So those are the two places I need to check. I need to check in the intervals then. I know that that's where my points of inflection are. So I do a sine graph, and the only thing I have to worry about is the cosine of t. And I am looking for, and it should be a negative cosine of t. I have the first interval where t is equal to negative pi over 2, and t is equal to pi over 2. My first interval starts from negative pi to negative pi over 2, because I'm constrained between negative pi and pi. My second one is from negative pi over 2 to pi over 2. And then my last one is from pi over 2 to pi. And again, the reason I'm doing those intervals is because I am constrained between negative pi and pi. That's told me what I was looking for. So I choose some angle between negative pi and negative pi over 2 that I know the answer of on my unit circle. What angle do you want to use in quadrant number 3 in reverse? What do you want to use?
3 pi over 4.
So I'm going to use t is equal to negative 3 pi over 4. Okay? So I have the negative of a negative number. So I have a negative of a negative number. What is that going to be then? And then I'm going to choose something in the interval between negative pi halves and pi halves. What do you all want to choose? We could choose 0. So I choose 0. The cosine of 0 is a positive number, but I have a negative multiplier out front. So what is that region going to be? Negative. I'm going to choose one other number between pi halves and pi. What do you all want to choose? 3 pi over 4? So I choose 3 pi over 4. And 3 pi over 4 is a negative number. When you take the cosine of 3 pi over 4 is a negative number. And I multiply it by the negative out front, so what is my region going to be? Okay, so here's my regions. Now, my first region is positive. That means I am concave up. My second region is negative, so it means I'm concave down. And my third region is positive, so I'm concave up. So what they ask for is the intervals in which I'm concave up or down. So I'm concave up in the intervals from negative pi to negative pi halves, union between pi halves and pi. And I am concave down in the interval between negative pi halves and pi halves. How was that? All right, so with that known and said, which one of these would you all like to do the second derivative on? B? Okay, cool. Do the second derivative on B to determine if you have any inflection points and the intervals of concavity, please. Just as a reminder, we can write this as x minus 4 raised to the 1/3 to help us with the first and second derivatives. Let's do the first derivative, g prime of x. What does g prime of x give me?
1/3 x minus 4 negative 3.
Okay, what is my second derivative then?
Negative 2/9 x minus 4 to the negative 1/3.
Now, if I set this thing equal to 0, I'm going to get negative 2/9 x minus 4 raised to the negative 5/3 is equal to 0. So this is negative 2 over 9. The third root of x minus 4 raised to the 5th power is equal to 0. If I multiply both sides by that denominator, I'm going to get negative 2 equals 0. So does this have any critical or points of inflection? No, there's no point of inflection. Because you got to be able to solve them. If you can't solve them, if you get something like a complex number or you get this false statement, that means that we have no points of inflection. No points of inflection.
Can you imagine if we just proved negative 2 equals 0?
I'm not going to do that.
Can you show why it's not 4?
You go back over.
Yeah.
Multiply both sides by the denominator. What happens when you multiply both sides by the denominator?
Still gonna get 0.
You get what? When you multiply both sides by the denominator? What happens to the denominator on the left-hand side? Cool? We cool? We cool? Okay. All right, so that's how we do these. The important thing that we get out of this also is the second derivative. The second derivative test, so we do the second derivative to determine if we have points of inflection, but the second derivative test gives us whether or not we have a maxima or minima without having to do the sign graph necessarily. So this allows us to look to see whether or not we have a maxima or minima. Now, if I take the second derivative, so the first thing I have to do is I have to locate my critical point. So I still have to take the first derivative, set it equal to 0, and solve. That hasn't changed. And then I do the second derivative, and once I do the second derivative, those critical points I put into the second derivative, and if it's greater than 0, then I have a minimum. If it's less than 0, I have a maxima. And it could be absolute, it could be local. Won't know until we look at what we have for all of our critical points and or the endpoints, if we have them. If my second derivative, when I put in that critical point, equals 0, then the test is inconclusive. And it doesn't tell us anything. So the first thing we always have to do is find the first derivative to find the critical points. And then we do the second derivative and put their critical points into the second derivative. Which one would you like me to do? B or D or C? B as in boy? Okay. So I'm going to do my first derivative. I have to do my first derivative, p prime of x. Do y'all want to do the quotient rule or the chain rule? Chain rule. So if I'm going to do the chain rule, I need to rewrite this as x minus 4 multiplied by x squared plus 20 raised to the negative 1. So I'm going to do the chain rule, which means I'm using the product rule. That means this u is x minus 4, u prime is just 1. V is going to be x squared minus or plus 20 raised to the negative 1. V prime is going to be negative x squared plus 20 raised to the negative 2 multiplied by 2x. In all of its glory. So P prime is going to be 1 multiplied by x squared plus 20 raised to the negative 1. And then plus x minus 4 multiplied by a negative 2x, x squared minus 20 or plus 20 raised to the negative 2. So there it is, the product rule and chain rule. So I'm just going to rewrite this so it makes it easier to see what the hell I have. So I'm going to rewrite this as 1 over x squared plus 20. And then I'm going to write minus 2x, x minus 4 over x squared plus 20 squared. Okay, so I just rewrote it so it made it easier. And in fact, I'm actually going to combine this because I need to do the second derivative. So if you are required to do second derivatives, if it's a little ugly algebraically, I strongly suggest you simplify before you do the second derivative. Because if you try to take the second derivative as it stands now, it is pretty gnarly looking. So I'm just going to clean this up algebraically. This side here, I'm going to multiply by x squared plus 20, just to have the same common denominator. Numerator and denominator by that. And again, the only reason I'm doing that is so I can just clean this up algebraically, because otherwise it could be pretty gnarly looking. And so I end up with x squared plus 20 minus, and I'm going to go ahead and distribute that negative 2x through. So it's going to be minus 2x squared plus 8x, x squared plus 20, the quantity squared. So I end up with negative x squared plus 8x plus 20 all over x squared plus 20, the quantity squared. Now I'm going to stop and let you all look at it and ask any kind of questions you may have. So I'm just going to stop. I'm going to pause it. The question was, this is being subtracted, and the reason it's being subtracted is because right here I have a minus 2x. And so it ends up becoming a negative 2x. And I could have wrote it as this, and that would have been okay too, is I could have wrote this as a negative and made that a positive, but I just pulled the negative out front. Anything else? Anything else? Okay, so now I'm going to set this thing equal to 0 and see if I can figure out some critical points. So I have 0 is equal to negative x squared plus 8x plus 20, x squared plus 20, the quantity squared. I'm going to multiply both sides by the denominator. And when I multiply both sides by the denominator, I am just in a land of quadratics. So I have 0 is equal to negative x squared plus 8x plus 20, which we like quadratics. I'm going to multiply everything by a negative 1 because I like to have my leading coefficient positive. It just makes it easier for me to factor this. And now I'm going to factor it. Factors of 20 that have a difference of 8. So x is equal to negative 2 and x is equal to 10. So these are my critical points. Those are my critical points. Once I found my critical points, I do need to do the second derivative. Chain rule or quotient rule? We're going to have to do the chain rule either way. Chain rule with product or chain rule with quotient? Product? Okay. So if I'm going to use a chain rule with the product, then I'm going to rewrite this as negative x squared plus 8x plus 20 multiplied by x squared plus 20 raised to the negative 2. So that tells me my u is equal to negative x squared plus 8x plus 20. U prime is equal to negative 2x plus 8. V is equal to x squared plus 20 raised to the negative 2. V prime is going to equal negative 2 x squared plus 20 raised to the negative 3 multiplied by 2x. Oh, Dallas, I'm feeling you, man. This is like the best thing I've ever done all morning. We haven't got to rotation of axes yet in trig. That's coming up. Yeah. It's coming. The best is set for last. Okay. So, I want to do, what was the function name on this? Was it, what was it?
P of x.
Okay, thanks. P double prime of x is equal to u prime, which is negative 2x plus 8, multiplied by v, which is x squared plus 20, divided by negative 2. And then plus, I'm going to have v prime, which is negative 4x. All I did was move that 2x to the front, multiply by the 2 that was there. X squared plus 20 raised to the negative 3, multiplied by my original function, which was negative x squared plus 8x plus 20. And there it is. I'm not going to clean this up algebraically, but what I am going to do is plug the 2 and that negative 2 and that 10 in there. So P double prime of 2, or negative 2, I'm going to put that in there. I'm going to get my calculator out, and I'm going to do negative 2 multiplied by negative 2 plus 8. And then I'm going to multiply it by negative 2 squared plus 20 negative raised to the negative 2 plus negative 4 multiplied by a negative 2, and then x squared plus 20 raised to the negative 3 multiplied by a negative 2 squared plus 8 times negative 2 plus 20.
We're plugging an x, we're plugging negative 2 to x squared. For x squared plus 20.
Yes. Yes, thank you. So that's what we're going to do. Now, I'm not real fond of doing all that hard work, even on my calculator. What I do know is that this is going to be a positive number, right? This is going to be a positive number. This is going to be a positive number. This is going to be a positive number. Because all I'm chasing is whether it's positive or negative. That's it. And then this is going to be negative 4 minus 16 plus 20. So this is going to be 0. Right? I'm going to put this in my calculator. But I'm going to just get a positive number. So negative 2 gives me a positive number on my second derivative. So by my second derivative test, if it's positive, it is a local minimum. So what I know with all of that work is at x equals negative 2, I have a minimum. To find whatever that minimum is, I do need to put that back into my original function to find out what the minimum value is. Now I do the same thing with the double prime of 10. So P double prime of 10. So when I put that in there, I'm going to get negative 2 multiplied by 10 plus 8. And then 10 squared plus 20 raised to the negative 2 minus 4 times 10 10 squared plus 20 raised to the, it's a negative there, raised to the negative 3, negative 10 squared plus 8 multiplied by 10 plus 20. And I'm going to do this, unfortunately, I can't just do it like I did before. What I have to do is I actually have to number crunch on this because they're not all the same sign. One of these is going to be larger than the other potentially. So let's just go through and see whether or not that second grouping here is going to be positive or negative, because I know that my first grouping is going to be negative. So I have a negative 4 times 10, that's a negative number. Yes?
Isn't that all the being zero?
No, not this time. 10 squared is 100.
But it's negative.
Negative 10? Wasn't it positive 10 and negative 2?
But there's a negative in front of the 10 squared. So
Right, right.
negative
So it's going to be a negative 100, yeah.
Plus 80 plus 20.
Oh, is that a 0 too?
Yeah.
Oh, cool. We love it when that happens. Thank you. So then we just have to look at this first one. This first one is going to produce a negative number here. This is going to produce a positive. So it's going to be a negative. So if it's a negative by the second derivative test, and I hope you all are writing these on your lovely note card, then it is a maxima. So at x equals 10, we have a maxima. And then I just have to put that 10 and that negative 2 back into the original function and determine what it is. Okay? How was that? Now, what I want you to do is an easy one. Thanks for allowing me to do that. So why don't you do A, please? A should be pretty straightforward and shouldn't take you all class. Okay, so we did the first derivative, g prime of x. When we do the first derivative, what do we get?
3x squared.
Okay, so when I set that equal to 0, what is my critical point?
0.
I'm going to do my second derivative, which is what? When I put 0 in there, what do I get? 0, so it's inconclusive. What it actually is a horizontal slide, so it's a critical point that has neither a maximum nor a minimum, but in this particular case, it is inconclusive because it equals 0. What do you think D, A as a constant, is going to do for us? Well, let's go ahead and do D. Let's do the first derivative. It is the chain rule, but the only thing I'm doing the derivative of is on x, so that's 1, so it's not a problem. I set this thing equal to 0. When I set this thing equal to 0, I get x plus a is equal to 0, so x is equal to negative a. Now I'm going to do the second derivative. So I'm going to get 12 x plus a raised to the 2. And if I put negative a in there, what ends up happening? It cancels, it gets me 0. So what's happening on this one? It's inconclusive. It actually is a turning point, and in fact, it is a, there's going to be an absolute, because it's a power of 4. This is an absolute minimum, but it's inconclusive. So if I were to put in h double prime of negative a, I get 12 multiplied by negative a plus a squared, which is 0. So the second derivative test is inconclusive on this. But I can tell you it's an absolute minimum at x equals negative a, because it's a power of 4. What this graph looks like, assuming this is a, is it looks something like this. So it actually is an absolute minimum. Okay, how much more do we have? Oh, carrying capacity. Sweet Jesus, that's cool. And sketching some graphs, that's even better. Okay, so let's just kind of blow through this a little bit. How are we doing about matching graphs? Because you know this crap's always on the test. I mean, this lovely is always on the test. Might even be verbatim on the test. How are we doing about matching graphs? A little shaky. So I would suggest, if you are a little shaky, to attempt this on your own, and then we can discuss it. Carrying capacity is one. Oh, this is actually perfect because of the whole coronavirus thing.
Oh, wow, yes.
When
Yeah.
we all started dying.
Yeah.
That's infection.
I usually do this. Actually, this is really cool because this is going to be happening in my Pre-Calc 1 class. There is a formula for these. And what it is basically is that if there's an illness out there that at some point, like the population of Chehalis, Centralia, say it's like 17,000 people, right? I think it's around 17,000. Somebody told me that last year, it's around 17,000. So if you have an infection out there and you're trying to determine how many people will get infected, you won't actually get all 17,000 people because there's going to be some people that never leave their house. You've seen them, you know them, it's your neighbor.
We have not seen them. They don't leave their house.
You've heard of them because you know the neighbor, you talk about them, they never come out of their house. They never leave the house. Groceries never get delivered, but somehow they're still in their house. You know what I'm talking about. And dogs are still getting missing. That's something else, though. When you also have some people that are going to be automatically immune to it. No matter what virus is out there, there's going to be some percent of the population that's going to be immune. So you're never going to get to this maximum. That is never going to hit 17,000 people. So if you have 17,000 people in this region, not all 17,000 will be infected with it. Now, you're also talking about, if you're talking about fish and wildlife and game, if you have a lake, it's only going to allow so many fish in that lake, and then you're not going to get any more fish. So if the carrying capacity of that lake is, say, 17,000 fish, you're never going to get quite 17,000 fish. Does that make sense? That's what the carrying capacity is. So here's a recap of derivatives. I would suggest that you read through that. Here's the guidelines for graphing these, and we're actually going to go ahead and go through the process of graphing these from beginning to end. Let me see. This stuff, yeah, it is a super long section. Which one of these would you like me to do, going through the graphing process?
Yes, we see.
Let's do C. Okay, so with C, the first thing I'm going to do is determine what the domain is. So I always determine the domain, and my domain is from non-inclusive 0 to infinity. Non-inclusive 0 to infinity. Always get your domain first. If you can determine your x and y intercepts, then you do that. Now this has no y-intercept because I don't get to include any y values. So then I might try to determine what my x-intercept would be. So if I can determine my x-intercept, I will do that. If it's too much work, then I'm just going to start jumping in and finding my derivatives. So I'm going to find, if I can do x squared natural log of x is equal to 0, then I'm going to do that. And the way I would do that is I'd say x squared is equal to 0, and the natural log of x is equal to 0. So the first part is, and what I'm using is I'm using this rule that says a times b is equal to 0. That means either a equals 0 or b equals 0. Those are your two choices. So if a equals 0, then it's not in my domain because I said that it couldn't equal 0. So the only one I really have to worry about is the natural log of x is equal to 0. Well, the natural log of x is equal to 0 when x is equal to 1. So my x-intercept is 1, 0. And I have no y-intercept. This is my x-intercept. And we have no y-intercept. Now I'm going to start doing my derivatives to determine if I have any points of inflection and also where my concavity is. So I'm going to do my first derivative. G prime of x is equal to 2x squared, or 2x, not squared, 2x, the natural log of x, plus x squared 1 over x. Now what I had was my original function g prime, or g of x, is equal to x squared, the natural log of x. U is equal to x squared, u prime is equal to 2x. V is equal to natural log of x, v prime is equal to 1 over x. So this is v, this is v prime, this is u prime, this is u. So what I have then is I have 2x, the natural log of x, and then plus just x. How was that? Okay. So I'm going to set this thing equal to 0, and so I get 0 is equal to 2x, the natural log of x, plus x. 0 is equal to, I'm just going to factor out an x, leaving me 2x, the natural, not 2x, 2, the natural log of x, plus 1 is equal to 0. The reason I'm going to do that is so that I can use that a times b is equal to 0 thing again. So again, I'm using the fact that a times b is equal to 0. So that means x is equal to 0, or 2 natural log of x plus 1 is equal to 0. But we know that x cannot equal 0, so we toss that one out right out of the gate. So the only one we have to worry about is 2, the natural log of x is equal to negative 1. The natural log of x is equal to negative 1/2. I'm going to write this in its equivalent exponential. So this is e raised to the negative 1/2 is equal to x. Write it as its equivalent exponential. So now I have my critical point. So I only have one critical point, and that's at e negative 2, e raised to the negative 1/2. So I found my critical point. I'm going to do my second derivative. So my first derivative, again, I'm just going to rewrite it over here, is 2x, the natural log of x, plus x. And I'm going to do my second derivative, so double prime of x. I'm going to have to use the product rule again, so I'm going to do the derivative of 2x times the natural log of x. So that's just going to be 2 the natural log of x. I'm going to do the derivative of the natural log of x times 2x. And so that's going to be 2x multiplied by 1 over x, and then just 1. So g double prime of x is equal to 2, the natural log of x, plus 2 plus 1. G double prime of x is equal to 2, the natural log of plus 3, natural log of x plus 3. Okay, so now I set that equal to 0 to see whether or not I have a point of inflection. So 2, the natural log of x plus 3 is equal to 0. 2, the natural log of x is equal to negative 3. The natural log of x is equal to negative 3 over 2. Turning this into its equivalent exponential, e raised to the negative 3/2 is equal to x. So that is my point of inflection. So I have my potential maxima or minima, and I have a point of inflection. So the next thing I'm going to do is I'm either going to draw the graph with, or draw my xy chart with x prime and y, or excuse me, I'm going to write either this, where I did before, f prime of x, f double prime of x. And I take my critical point and my other one, so my first one would be e raised to the negative 1/2, or e raised to the negative 3/2, and e raised to the negative 1/2, and determine whether or not I'm concave up and concave down from these, and whether or not they're increasing and decreasing. That's these graphing by hand. Now, on the test, this is too much work for 50 minutes. If this was a 2-hour class, then I'd probably give it to you as on the test. This is too much to do on a test. So what I may ask you for is finding critical points, points of inflection, or I may give you the information and ask you to draw the graph from that, because you only got 50 minutes to do the test.